All right, so in this problem we'll examine a situation where we are going to look at conservation of momentum to see, to predict or look back at a situation and see how was one part of our system moving given how we observed the system move after the collision. So here's what happens. Just before the collision, right? So the spacing of these things doesn't really matter here. What we're saying is like, I need room to draw my arrows to indicate they're flying at each other. Just before the collision, we know that we got two masses, in this case meant to represent two people running at each other. They're going to collide. And one has a certain amount of mass, it's moving to the right. One has a certain amount of mass, and it's moving to the left. So we use some variables to indicate the initial velocities of both of these and indicate their masses. Just after the collision, right? So they're running at each other, they hit, and now we care about just after. In this case, we're assuming that the two people in colliding sort of become a tangled mess, and then just after the collision, as a tangled mess, they're going to move off in one of the directions. In this case, we observe that when they smash into each other, they end up moving to the left with some new velocity that's associated with that tangled group of people now moving. To add a little bit of flair to the problem, we also note that a long time after collision, right, this here only cares about just before they hit and just the moment after they hit. Well, we're going to assume that after they collide and now are sliding away, they end up sliding along the ground. And so relative to the point where they collided, they slide a certain physical distance and then they come to a stop. The reason we'll use this piece of information is that if we know the amount of frictional force that say the ground would apply against them sliding, and we know how far they travel, that's going to tell us, well, how fast were they traveling, or how fast were they moving just after they collided in order for them to slide by a certain distance. So, in order to examine this problem, we break down and we say, okay, we got two masses, and before the collision they're moving in some way, and after the collision they're moving in some way, so we can account for the momentum of both of the objects before and after. So here, I write out fully mass of object 1 times its initial velocity as a vector, so direction matters, mass of the object 2 times its initial velocity, and then after the collision happens, we care about the mass of object 1 and its new now final velocity, and the mass of object 2 and its new now final velocity. First thing we can do is we can simplify away some things. In this case, the initial masses and velocity, we can't do anything with this side, but we do know that both of the objects after the collision are moving with a common velocity. So that means we don't have to have two separate terms. Instead, what we can do is we can say, okay, well, this new velocity, this new final velocity, whatever it is the velocity on both of these, so why don't we pull it out? So now we have all of this mass is now moving away with this velocity here, this new final velocity. So now we've been able to take, instead of having two velocity terms on this side, we turned it into one velocity term. Then we go in order to have some numbers to work with, we note that, all right, this floss here, or this mass here is going to represent some guy who's 70 kilograms. This here is a much larger person. They're a hefty 200 kilograms. We're going to say that the 200 kilogram person is running at a brisk 6 meters per second to tackle the other person. Just after their collision, after the collision, when they smack into the ground and slide along, we're going to assume they slide along the ground by about 1.5 meters. And then the coefficient of kinetic friction on whatever it is they're sliding on will just be 0.5. So what we can do then is, after we've set up our full expression for conservation of momentum, then we plug in all the numbers and then identify the unknown we want to solve for. In this case, the one thing we're not given is what is the initial velocity that this person was traveling at just before the collision occurred. So since that wasn't given to us, hopefully we're given enough information we can solve for that. So what we do, we go to this expression, we start plugging in numbers. The mass 1 is, of course, the 70 kilograms. The mass 2 is 200 kilograms. The sum of those would then, of course, be 270. We don't know how fast the smaller person was initially traveling with, so right now that variable is still left as a variable. We do know how fast the larger person was traveling, 6 meters per second. Look. Note that because momentum is a vector, direction matters. So if we take traveling to the right as being positive, then that means in order to talk about this person traveling 6 meters per second to the left, we have to put a negative here. So can't forget that negative. Then we go, okay, so we got our 270 because that's the sum of those masses. We then take the numbers and we plug them into this formula here to solve for what would have been the velocity these two would have had to have been traveling at just after the collision in order to slide. If you plug in those numbers, we get out the value 3.834 whatever, but again, this is a velocity acting to the left, which means, again, we're going to have to put a negative here. So, if we multiply this all out, and we multiply this out and move it to the other side, and then we divide by the number 70, note this mass and pull it down here, we ultimately find that when we solve off the numbers, first off, we get a positive number, which is good because our problem assumed that the person who's 70 kilograms is running to the right. If we did our math and we got a negative number here, then that would mean that something in our, either we did the math wrong or we made an incorrect assumption about what is actually happening in this problem. Because sometimes it would be the case that you'll solve for a value, right, for some arbitrary situation, and out will pop a negative number. And what that negative number would tell you, if the negative number was correct, is that, in this case, it would imply the guy was running off to the left instead of running to the right, which is what we're assuming happens. So he's running to the right at the 2.35 meters per second. The other guy's running to the left at the 6 meters per second. And that collision and them sticking together then results in them sliding by this, hitting the ground, sliding by the certain distance. So that's all we had to do. We threw up a conservation of momentum expression, accounted for all the particles, accounted for all their velocities, all the masses, solved for the one thing we wanted to know about. Now, another thing that we can determine with one additional piece of information is how much force was actually applied to the people involved in this collision if we know how long it takes for the collision to actually occur. Now note in this case when I say how long it takes for the collision to occur, I'm not talking about the time between when they're running at each other all the way to when they slide and come to a stop. I'm saying the collision occurs, even though here we're just saying they're coming together and the next moment they're stuck together. But in real life that takes time. Think for example like a car collision. It's not as if you go from a moving car to a smushed car instantaneously. If you've ever seen the slow motion footage, there's that time where the car is crumpling up and hitting the wall. So it takes time for a collision to occur. And that time affects how much force there actually is being imparted to the object. Well, in this case, we know that the force that something experiences is based on how much its momentum changes and the amount of time that goes by. So in this case, we're going to assume that this collision occurs in about 1/10 of a second. That is, big guys running in, big guys coming in, hits the other person. The actual part where they become a tangled mess is really short, fraction of a second, and then later on they slide. All we care about right now is what's happening in that fraction of a second when they hit each other. This change in momentum term, also called the impulse, is just what's your final momentum minus your initial momentum. How much is your momentum changed? Now in this case, the final momentum of the person who's been, of this person here, is based on the fact that, well, even though after the collision, his body's all tangled up with the other person, he still has a certain amount of mass traveling at some velocity. So the final momentum would be his 70 kilograms times how fast the combined mass is moving. Then his initial is what we just calculated here. His initial velocity, which again we multiply by 70. Note the way I've written this, because there's a set, the m is on both terms, I went ahead and pulled that 70 kilograms out. But here we have his final velocity and his initial velocity. Subtract them, multiply by the mass, divide by the amount of time that goes by, and that gives us, in this case, the number 4,000. Now, I'm putting harder here because I want to be careful here because I left the negatives on these because force is also a vector, and so direction matters. So technically, this number should be negative. It's negative 4,000 newtons worth of force. The negative force makes sense because you can envision that if to the right is positive and to the left is negative, then if mass 1 was moving this way and later on I wanted it to be going back that way, I would have to exert a force that is directed to the left, or a negative force in this situation. To give some context, that 4,000 newtons, a little over 970 pounds worth of force imparted to a person, which may seem like a big number, but when it comes to, if you look up some football statistics, those players will routinely be having impact forces of like 1,600 pounds. So this isn't and while it's a big number, it's still consistent with something that can physically happen. So again, to summarize, we can look at some scenario and say, all right, we know something about the masses and velocities before a collision and the masses and velocities after a collision. At the same time, we can also use other information that may come about later, in this case, this thing sliding by a certain distance, and we can use that information to calculate some of these things that, even if we're not directly given what this velocity is, we can figure out this velocity from other information. We write out conservation of momentum. We keep track of all the momentas, make some simplifications if they're available. From there, we could either symbolically solve around, get an expression for the quantity we want, or in this case, if we're solving for this and we know all the other quantities, we can just pop in the numbers that we're given, solve around, and then just numerically solve for the thing that we want. And then this idea of momentum is connected with an idea of the impulse and the amount of force that something can experience. So if we know how much the momentum of something changes, and we know how long it actually takes for some collision to happen, or some force to interact with something or whatever, then we can figure out the size of that force based on how much the momentum has changed and how much time has gone by.